All right, let's talk about something that's happening all around us, like right now, but we barely ever notice it. It's kind of like nature's own little magic trick. Yep, we are talking about evaporation. Have you ever wondered about this? After a big downpour, there are petals all over the place. But then you look again a few hours later, and they vanished. Poof, gone. So where did all that water actually go? Did it just soak into the ground? Well, that's part of the story, but not the whole thing. See, it's not some kind of magic. It is pure, amazing science. And to really get our heads around it, we're going to start with something super simple, something you could literally do in your own kitchen, a bowl of salty water. Believe it or not, this is going to explain everything. Okay, so let's put on our detective hats. Our first mission, should we choose to accept it, is to solve the case of the vanishing water. And like any good investigation, we've got to learn the lingo first. There are just 3 key words we need to lock down. First up is the solute. That's just the solid stuff you're dissolving, the stuff that looks like it disappears. So for us, the solute is the salt. Easy peasy. Then you've got the solvent. This is the liquid that's actually doing the dissolving. In our little experiment, the solvent is, you guessed it, the water. And what happens when you mix them together? You get a solution. That's the final mixture once the solute has totally dissolved in the solvent. So salt plus water gives us our saltwater solution. Makes sense, right? Awesome, because now we get to the really cool part. All right, let's zoom in, way, way in. We're going to shrink ourselves down to the microscopic level and dive into this solution. Because what looks like a totally still bowl of water to us is actually, well, it's basically a giant chaotic dance party for particles. I'm not kidding. Inside that water, there are billions and billions of tiny particles, and they are never, ever still. They're just constantly jiggling, bouncing off each other, and zipping around, non-stop. So what happens if we add a bit of energy to this party? Say, some heat from the sun. Well, that gentle jiggling, it turns into a full-on frenzy. The particles get totally energized and start whizzing around like crazy, moving way, way faster. And with all that extra energy, the fastest particles, the ones right at the surface, can do something incredible. They get moving so fast they can literally break free from all the other particles holding them back. They just escape. They leap out of the liquid and into the air, turning into a gas. It's the Great Escape. And that whole process, that has a name. It's called evaporation. And here's the really important bit. This happens at temperatures below the boiling point. This isn't the same as boiling a kettle. It's a much slower, kind of sneakier way for a liquid to turn into a gas. Okay, so the water particles can escape, but what about the salt particles they were mixed with? They get left behind. And this leads to a really practical use for evaporation. We can actually use it to separate things and get our original stuff back. So picture this, we're in a science lab. We take our salt water and pour it into a little dish. Then we heat it up gently, maybe with a Bunsen burner. You can literally watch as the water level goes down, 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 because all those water particles are getting energized and flying off into the air. And then, what's left behind? Just the solid salt crystals. We did it, we got the salt back. Okay, that worked, and it was super fast, but what if we didn't use all that intense heat? What if we just let it be? What happens if we just wait? Well, that brings us to something that's less about speed and more about art. The art of crystallization. This is the slow and steady wins the race version of what we just did. And you'll see that slowing things down can have a really beautiful outcome. So instead of a Bunsen burner, let's take that same salty water and just stick it on a sunny windowsill. The sun provides a little bit of gentle warmth, just enough to give those water particles the energy they need to escape. But it's going to happen way, way slower. Not minutes, we're talking maybe a couple of days. So a few days pass, the water is all gone, and, just like before, the salt is still there. But here's the cool part. When you look at the salt this time, it's different. The crystals aren't those little powdery grains we got before. No way. They're bigger, much bigger. And this shows us a really fundamental rule of thumb. It's a key idea. When crystallization happens more slowly, the crystals can grow bigger. It's like your patience is rewarded with these amazing, larger crystals. But why? Why does going slow make bigger crystals? Let's connect all the dots now and figure out why patience really is a virtue, at least when it comes to this stuff. This table really lays it all out. On one hand, you have fast evaporation. You're blasting it with direct heat, it's over in a few minutes, and you get these tiny little crystals. On the other hand, you have slow crystallization. You're using gentle warmth, it takes days, and you get big, beautiful crystals. The reason is that the slow method gives the salt particles time to line up and organize themselves into these larger, more perfect structures. It's the same basic process, but changing the speed totally changes the outcome. And just to be super clear, let's go back to those puddles. They are definitely not boiling away on the street. Water boils at 100 degrees Celsius, which is really hot. Evaporation is what allows water to turn into a gas at normal, everyday temperatures. It's the secret behind how things dry. You know, this whole thing is so much bigger than just a lab trick or a disappearing puddle. What we just saw in that little bowl of water, it's a tiny model of a massive process that literally powers our entire planet. It's happening everywhere, all the time. Think about the water cycle. This is it in action. Water particles are constantly escaping from the surface of oceans, lakes, and rivers. That invisible water vapor rises up, it cools down, and it forms clouds. And of course, that water eventually comes back down as rain, and the whole cycle starts again. Without this great escape of evaporation, we'd have no clouds and no rain. It's that important. So, when you boil it all down, here's the big takeaway. Controlling the speed of evaporation completely changes the outcome. A fast, frantic process gives you one result, small crystals. A slow, patient one gives you something totally different, big crystals. And that makes you think, doesn't it? Where else in nature, or even in our own lives, does a simple rule apply? That the speed at which something happens completely changes the final result?